Swayam Prabha. Digital India. Educated India.
Minus plus, feedback is on the minus side, and here is our component capacitor. All right, and here is a resistor. So this is V input, R, let's call R and C. Let's say this is the node X. So you can quickly go through the expression. The capacitor in Laplace domain, we know that its impedance is 1 over SC. Okay, so V out over V in, you can convince yourself, is equal to the impedance in the feedback, which is 1 over SC divided by impedance input, which is R. This comes from the same expression as R2 over R1 that we did earlier, and the negative sign. So this R2 part is the impedance of the capacitor. Okay, and we can see that it is minus 1 over RCS. The 1 over S term represent integrator. Okay, and that is in the Laplace domain. Other way to look at this is also, you can say, you can just go through brute force differential equations that you are familiar with. So what would you do in that case? You would say, hey, V in divided by R is the current which is going to flow here, and that same current will flow through this capacitor, right? So that would be equal to minus C, and once there is current flowing through the capacitor, then your voltage will change. So C dV out divided by dt. That's the equation. I is equal to C dV by dt, right, for the capacitor. So if you look at this particular expression, then you can say that, hey, dV out by dt is equal to minus 1 over RC times V in. Hence we can say V out is equal to minus 1 over RC integration of V in with respect to dt. And this is the integrator operation that we are all familiar with. So this is all kind of review for you, but I'm going through it intentionally a little bit slowly in case your basics are a little bit rusty. So go through this one more time if you have forgotten. Now what does integrator really represent? 1 over S. So 1 over S represents at S equal to 0, this value goes to infinite, right? So the integrator represents pole at S equal to 0. Okay. So let me take a slight detour regarding poles and zeros. Okay. As I said again, if there is a pole if the expression has 1 over S plus A term, then at S equal to minus A, we have a pole. Because at that point, it will go to infinity. However, if you have term S plus A divided by something else, then in the numerator, then S equal to minus A, you have a 0. And what does 0 really mean? 0 means that at that point, the expression actually goes to 0. S equal to minus A frequency, expression goes to 0. Okay, so that's what we talk when we talk about pole and 0. That's what it means. Now the impact of I'm going to assume right now that you have done some sorts of Bode plot for all these. If you have not, don't be afraid. We are going to do a separate lecture for you as a review lecture for Bode plots. So go through that, and that should take care of the, I mean, it should be basics for many of you, but in case you have not done it before, you can go through the basics of the body plot. We will also provide some background material for the body plot. Generally this is done in the previous classes, so we generally don't cover it in this particular class. Okay, so what is this is the ideal expression. Okay, V out over V in is equal to minus 1 over RCS. So here you're assuming that op amp has infinite AV gain. Okay. Now, if the op amp has limited gain, let's say AV, let's see what happens. What you can do is, I'm going to redraw the circuit one more time and go through the analysis in a little bit brute force manner so that you understand. Okay, so this is our V in, let's call this node X, and this is our V out. And this is a capacitor C, this is resistor R. So V in minus Vx divided by R is equal to Vx minus V out divided by 1 over SC. That's our expression, right? Also, we know that op amp has finite gain, which means Vx is equal to minus V out divided by AV. AV being the open loop gain of the operation amplifier. Once we know that, then we can substitute here, and then you can quickly substitute here, and I would like you to, I'll give you 10 seconds. You can pause the video here and go through the expression and write the expression for the V out over V in. Just substitution, solving the equation. Okay, so if you have got it right, then V out over V in is equal to minus AV divided by 1 plus AV RCS. Okay, so what does this look like? This expression look like? What is it telling you? Okay, so let me make a comparison. A comparison would be, simple comparison would be, compare this with something that's, I'm just using two different terms, 1 plus S divided by P1. This transfer function. Compare these two transfer functions. Right now we are ignoring the negative sign, okay, because the negative sign just gives you phase shift. Okay, so if you look at the gain, compare these two gains, then what is this telling you? This is telling you that our expression is going to look like, originally, if I compare these two, then ADC is equal to AV, that's our large gain, okay, and the location of the pole, now we have a pole location P1, which is equal to 1 over RC 1 plus AV. Okay. There is a reason I'm making this point to you. So it will all fall in place if you bear with me just for a second. Okay. So let's say we take a simple example of a resistor and a capacitor. Okay, R and C. So this is my V in and this is my V out. So in this case, you know how to derive this. V out is equal to divided by V in, that would be equal to 1 divided by 1 plus S RC. This should be pretty straightforward. So now we can compare these two and see what's really going on. We know that this represents a first order low pass filter, and what that means in frequency domain, we see characteristics that looks like this. Okay. So this particular expression would also show a characteristics looks like this in the body plots. All right. So let's go back and put all these things together on body plot. Okay. As I said again, the basics of the body plot we are going to go through separately with you. So what are we doing? We are plotting log of f, frequency on the x-axis. And on the y-axis, we are plotting the gain in dB. Okay, what does dB mean again? It's 20 log of the number, whatever that gain number is. All right. Now, if you look at the ideal integrator, the expression was 1 over S RC. If you look at the mod of that expression. Okay. What this means is there is a pole at 0 frequency, which means that at 0 frequency, which means as you keep going closer and closer towards origin, the gain is infinite. So this value will be infinite. And since we are plotting logarithm of f, generally we cannot plot origin on this particular plot, and what you would see then is your gain. I'll use a different color for the ideal body plot. Ideal integrator would look like this, something like this. Okay, and so S equal to, at frequency S equal to 1 over RC, gain is 1, and in dBs that would be equal to 0. So this is your 0 on the dB axis. So 1 divided by RC is the unity gain frequency. Let's modify this slightly, and what we will call, instead of f, we will call it log of omega. Otherwise we have to put 1 over 2 pi over here. S equal to j omega, right? That you know. All right. So this is the body plot or gain plot of ideal integrator. It just looks like a straight line, and the slope is 20 dB per decade. All right. Now, if you look at the effect of finite gain of the op-amp, then what happens? So we said that the expression is this right here, which is right here. So what this is telling you is that the DC gain or low frequency gain is equal to AV, which is the open loop gain of the amplifier. And that could be, in this particular case, I'm going to draw it in a green, and it looks like this, something like this. So this would be, the green is going to be our op-amp based integrator with finite gain. So this would be 20 log of AV. All right. And then this particular frequency that we are talking about would become then your first pole that you encounter, which is equal to this pole frequency P1, which is given by this particular expression. Okay, so we can say that this frequency omega here, this is equal to 1 divided by 1 plus AV times RC. That would be the first pole, P1. All right. And let's plot our simple RC filter on the same plot, and in a different color. Let me use a maybe blue color here, and you would immediately see that the DC gain here is 1, okay, 0 dB. However, the location of the pole is 1 over RC. So the location of the pole is same as earlier, and you can easily plot the curve then. It looks like this. Something like this. I'm drawing them separately just so that you can identify all three of them. So the green part would look like this. So let me recap again. The magenta curve, this one is the ideal integrator. And there, if it's 1 divided by SRC, the 1 over RC will represent unity gain frequency of that integrator. And at S equal to 0, you have a pole, so this curve will approach towards infinity as you go close to 0. And as I said again, we are plotting log of omega here. Okay. The green curve, which is shown over here, represents effect of finite op-amp gain, AV. And you can see that instead of going all the way to infinity, now you're limited to 20 log of AV. The 1 over RC part still stays the same, the unity gain frequency of this particular integrator. And the blue part, what I'm showing you is actually just an RC filter. The interesting part of RC filter is the DC gain is 0 dB. Okay. So there is no gain provided. The corner frequency is still 1 over RC, which is unity gain frequency. It's not really unity gain frequency, actually it's a pole frequency now, because as soon as you go close to it, it will drop by 3 dB. At the pole location would be still 1 over RC, and at that pole location, the gain would drop by 3 dB. Okay, so this is in a nutshell how we compare the three particular cases. One is ideal integrator, then the integrator with effect of finite gain of the op-amp, and the third thing we plotted a simple RC filter on top on the same lossy integrator. We call this a lossy integrator. So okay. Similarly, we can do analysis for differentiator circuit. So as you would have guessed it, whatever you do in the integrator, you flip the components and you should get a differentiator. And let's try that out and see what happens. So in this case, instead of a resistor, we would put a cap, and then we would put a resistor here. Minus plus, remember minus sign over here, otherwise it will be a positive feedback. So this is capacitor C, Vx, R, and V in and V out. So I would leave it to you to prove it to yourself that V out divided by V in, first of all, is minus RC times S. So S is in the numerator, which means at S equal to 0, there is a 0 of this expression. Okay. So at S equal to 0, since the term is 0, the log term will go to minus infinity. We can also do the differential equation expression, and you will see V out is equal to minus RC times dV in divided by dt. And if we do the same finite gain analysis, you will see that V out divided by V in is equal to minus SRC AV divided by 1 plus AV. This is something that I expect you to do on your own, but I'm just writing the expression to make a point. And follow the same trick that we used before. Divide by RC. So what does this slightly complex expression tell you? This is telling you that the 0 is still at origin. However, there is a new pole introduced in this circuit, and that pole is at 1 plus AV divided by RC. That's the pole location, P1. in this case. And let's, as we did before, we will also compare this with RC network, where this is V in and this is V out, and this is a capacitor, resistor. So you can say that V out is equal to SCR divided by 1 plus SCR. And now we are going to compare all three of them on the same plot, in the body plot. All right. So if you do the body plot now, it will look like this. And here we do log of omega. Omega is the radians per second frequency. It's plotted in the log scale, and the gain is in dBs, which is 20 log of gain. Okay. So if you look at the ideal integrator, we see minus RCS. Okay. So what we expect is, we expect at S equal to 0, there is a 0, which means, let's use the same convention, let's use this particular color. So this would represent ideal differentiator. So this is 0 dB. And as you would have guessed, at S equal to 1 over RC, you will have 0 dB frequency. So this would be 1 divided by RC for the ideal differentiator. Okay. So just this one particular intersection will define this differentiator circuit. As soon as we look at effect of op-amps finite gain AV, what we see is 0 is still at origin, so that part remains the same. However, there is a pole introduced at this particular frequency, 1 plus AV divided by RC. So what you would see then is, if you plot the characteristics, you should see something flattening out over here. Everything else remains the same, and the pole frequency is 1 plus AV divided by RC, and this is 20 log of AV, open loop gain. And the third thing we talked about is the blue part, which is lossy differentiator, something that looks like this. And then it will flatten out over here, something like this. The blue part is going to be, this would be your RC differentiator, this would be your op-amp differentiator, and the magenta would be ideal differentiator. Okay. So the concept of frequency response we are going to slowly introduce, and what I would expect, if these plots that I am showing you, they are not making sense to you, then you should go through and review the body plot related material that we are going to give you. We will give you a online tutorial and also some links to very simple material that's easy to digest on body plots. Okay. Thank you.